Hi everyone, welcome to Mathemly.
Welcome back to our neural network series. So far, we have seen how data flows forward through a network, how a prediction is made, and how the loss function measures how wrong that prediction is. But now comes the most important question of all. How does the network actually learn from its mistakes? The answer lies in a powerful concept called backpropagation. In this video, we will break down backpropagation step by step and see how error flows backwards through the network, telling each neuron how to adjust its weights and biases. So let's dive in. In the previous video, our network made a prediction for a house price and then used a loss function to calculate a loss value, a single number that told us how far that prediction was from the real price. But knowing how wrong the prediction was isn't enough. The network now needs to answer two important questions. 1. Which weights inside the network led to this error? 2. And how should they change to reduce the error next time? Remember that the final price prediction wasn't produced by one neuron. It was the result of many layers and many weights working together. That is where backpropagation comes in. It takes the final error from the loss function and sends that information backwards through the network, layer by layer, assigning responsibility to each weight and bias. This is the bridge between measuring a mistake and actually learning from it. Backpropagation literally means propagating the error backwards. In forward propagation, data flows from the input, like house size, location, and number of rooms, through the network until we get a final price prediction. But once we calculate the loss, say the network predicted $280,000 instead of the actual $300,000, the direction of information flow reverses. Now, instead of asking what is the prediction, the network asks where did this $20,000 error come from? The output neuron goes first. It looks at how far its prediction was from the real price and sends a feedback signal backwards. Each neuron along the way asks a simple question: how much did my output contribute to this final error? Some neurons had a strong impact. They pushed the prediction too high or too low, and some had only a minor effect. By the end of the backward pass, every neuron and weight knows how responsible it was for the mistake. This is the conceptual foundation of backpropagation, as it assigns credit and responsibility for the error to every part of the network. Now that each neuron knows how much it contributed to the error, the network can finally take action and update its weights to improve future predictions. Let's stay with our house price example. The network predicted $280,000 while the true price was $300,000. During backpropagation, each weight receives a signal that tells it the direction it should move. Every weight effectively asks, if I were a little larger, would the prediction move closer to $300,000 or would it move further away? Under the hood, this decision is guided by mathematics from multivariable calculus through a method called gradient descent. Gradient descent tells the network how the loss changes when each weight changes, in other words, which direction increases the error and which direction decreases it. Backpropagation uses these gradients to effectively compute how every weight and bias should be adjusted to reduce the loss. If increasing a weight would help reduce the error, the network slightly increases that weight. If increasing it would make the prediction worse, the network slightly decreases it instead. These adjustments are intentionally small. The network doesn't want to overreact based on a single example. Learning works best when changes happen gradually. After the weights are updated, the network runs forward again with these new values. Maybe this time, the prediction improves from $280,000 to $290,000. By repeating this cycle, predict, measure the error, and adjust, over thousands of examples, the network steadily improves. step by step, its predictions move closer to the correct house prices. When the network updates its weights, an important question comes up. How big should each change be? That is exactly what the learning rate controls. You can think of the learning rate as the step size the network takes when adjusting its weights. If the learning rate is too large, the network takes huge steps. Instead of moving closer to the correct house price, it might jump past it, overshoot, and become unstable. If the learning rate is too small, the network barely moves at all. It may be heading in the right direction, but learning becomes extremely slow and inefficient. A well-chosen learning rate finds the balance. It allows the network to take steady, controlled steps that gradually reduce the loss and improve predictions over time. So now, all in one place, backpropagation doesn't happen in isolation. It isn't just one neuron learning at a time. The entire network learns together. When the error flows backwards, each layer receives a signal from the layer ahead of it. This signal tells the layer how much the final prediction needs to change. At the same time, each neuron considers how sensitive it is to that error. Some neurons play a bigger role in shaping the output, while others have a smaller influence. Using both pieces of information, every layer updates its weights in a coordinated way. This collective adjustment allows the network to reshape its internal representations, how it understands inputs like house size, location, and number of rooms. After many repeated cycles of forward propagation, loss calculation, and backpropagation, the network gradually becomes better at mapping inputs to accurate outputs. Learning doesn't happen all at once. It emerges from many small synchronized updates across the entire network. To sum up, backpropagation is the learning engine of a neural network. It takes the error measured by the loss function and sends it backwards, telling each weight and bias how to adjust themselves. This process, repeated thousands of times, is how neural networks learn from data, correct their mistakes, and improve their predictions. But as networks become deeper, the gradient-based updates used in backpropagation aren't always perfect. Sometimes the updates become too small, sometimes too large, making learning slow, unstable, or even impossible. In the next video, we will explore these challenges and build intuition around why they happen and how modern optimization methods try to overcome them. So until then,
If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.